Hi, my name is Thomas. I'm a product manager at Salsita, and I will talk about the Bitcoin technology. First, a disclaimer. Louder? Okay. So, a disclaimer. I'm targeting a tech-savvy audience, people who know little about Bitcoin and who wanted to but never got around to delve deeper into the technology it uses. I'll talk about the concepts and tricks used by Bitcoin that you can find elsewhere as well. I will start addressing the problem of remembering passwords. Then I'll be a bit more philosophical, and I will talk very briefly about distributed systems and why they are so difficult. And finally, I will be slightly more technical and mention checksums and compound verification. Part 1, remembering passwords. We are using many websites to which we log in with credentials. We want to stay safe, so we don't reuse the same password, of course. And we have a unique password for every service. This, however, leads us to overwhelming our memory with random passwords. So what do we do? Naturally, we use a password manager, all of us. That saves us from the cognitive overload. And since we need to only remember one master password, it's quite easy, and we are set for life. Now about Bitcoin. Just a quick refresher. The Bitcoin consists of blockchain and addresses and wallets. The main building block is a blockchain, which is a humongous list of transactions. A transaction is something like 0.3 Bitcoin has been moved from address A to address B. And then you have these addresses. In terms of asymmetric cryptography, address is the generated public key, and the private key is the password. It allows you to manipulate Bitcoins at that address. These addresses and key pairs are very simple to generate, and there are many websites that allow you to do that. Also keep in mind that addresses like passwords and password managers aren't to be reused. A collection of these pairs is called a wallet. So now you have an address and a password. You can simply print these out and you're set. Or are you? Unfortunately, it's not very secure to keep all the key pairs printed out, and it's kind of impractical to have a collection of those somewhere. There's a better way, and it's akin to what password managers do. Say hi to seeded wallets. The idea is very simple. You have one seed, which you can iterate and keep generating key pairs. The seed, in this sense, represents your whole wallet. Now you only need to remember the seed. It's at least 128 bits of entropy, and that's not easy to remember still, right? So what's the solution? The idea here is a memoized list. So imagine there's a public word list of 248 words. This number doesn't sound very random, does it? In fact, every word represents a number between 1 and 248. In other words, it's like 2 to the power of 11. So now I guess you know where I'm getting. If you have 128 bits of entropy and then some 4 checksum bits, you only have to remember 12 words, or in other way, like 132 divided by these 11 words of entropy generated by each dictionary word. So I can show you an example of a real wallet. You can see the list like Stone, Dentist, Mutual, Nose, Dignity, etc. This is quite easy to remember, and while looking quite innocuous, it holds you all your bitcoins you have and you own. So now let's talk about something more philosophical, which is distributed systems. Communication in distributed systems is very hard, and consensus is even harder. Just to clarify, by consensus I mean mutual agreement of all the nodes on one single state. There's a very nice schoolbook example that demonstrates exactly that. So picture you have two armies, A1 and A2, who want to attack the city. As you can see, both armies have fewer soldiers than the city. Their attack is only successful if it's coordinated. Since they are separated by valley, they can only send messengers to each other. Messenger can be captured by the city defenders. How do they agree when to attack? So let's play out a simple scenario, and also keep in mind that these two generals could have pre-agreed on the protocol. So say General A1 sends a message, attack at dawn. He doesn't know if the messenger got through or was captured. So he can wait for the confirmation message from A2. So imagine that the messengers who went through and got to A2, and now A2 is sending back a message. So he sends the messenger back to A1, but now A2 doesn't know if the messenger was received. So A1 again needs to send another confirmation, etc., etc. And if you keep going this way, you notice that this doesn't solve the situation, because there's still like one more confirmation that needs to be made. So the TLDR version is that it's impossible for them to reach a consensus. To add insult to injury, imagine there are multiple generals. Some of them are even bribed by the city and want the attack to fail. So how do you manage a consensus there? It's tricky, right? I guess we all agree. And now let's go back to the real world where these things just manifest themselves. You can see it everywhere. Let's talk about microservices. This is one of the reasons why microservices are tricky, because you cannot agree on this simple fact. Or let's talk about TCP, which is we can view it as a consensus protocol, where there's a sender and a receiver, and they need to agree on which is the last packet that was sent and received. So in case of TCP, it was solved by brute force. You just resend the unconfirmed packet after some timeout, regardless whether it was captured. Bitcoin is even a little bit trickier, because agents have a vested interest in skewing things in their favor. Bitcoin is money, and people want to have money. Bitcoin, I won't delve very deep into this, but the idea here is that Bitcoin solves it with a probabilistic consensus. Since we cannot solve it for sure, we can just put some probability into it and say, like, we are 99.59% sure that this is the current state of the blockchain. Plus, compounding it with the fact that it's very, very, very hard to create a block in a blockchain, it makes it very hard to undermine and forge the whole thing. And last but not least, let's talk about a more technical topic, which is compound verification. I guess you encounter this every day. You have some files, and you just need to know the integrity is there. So what you do, you generate a checksum, which is just another word for a hash of the contents of the file. This serves as a verification that the file wasn't tampered with. We can observe it when we do a system update, or even when we run npm install or any other package manager you like. So this was all well and very simple, but how about compounding this? What we wanted a single checksum that would ensure that multiple sources and multiple consecutive items are intact. Introducing the hash pointer. Compared to regular pointer, which is just a random address for some data, hash pointer ensures the data integrity because it's calculated from the data. In other words, every different piece of data can have a computable address, which is the hash. I thought of 2 examples how these hash pointers are compounded into more complex data structures, and I could name like 2 technologies that are using it. So the more complex data structures are linked list and a tree, and the technologies that are using it are Bitcoin, of course, and Git. So let's look into the LinkedIn example. Linked list, not LinkedIn, sorry. Thanks, Razi, for doing this. So imagine every item or block of data uses a hash of the previous item. This way, if you tamper with the data of one block, it changes its address, and the follow-up block is invalid, since it points to something else. This is what both the blockchain and Git commit history look alike. With Git, every commit object contains a hash pointer to all its parent commits, and in Bitcoin, every block contains a hash pointer to the previous block. Now let's really briefly talk about the trees. You might be familiar with the Merkle tree concept. And that's used when the data structures are kind of tree-shaped. One example is, again, in Git, the project file structure. Or even, when it comes to Bitcoin, we can talk about transactions. I honestly don't know why they need to be tree-shaped, but they decided to kind of couple them and just build up a tree out of transactions in every single block. Now, for us, the only thing you need to remember is a tree root. And that ensures if the tree root checks out, it means the whole tree is intact and well constructed and not tampered with. This provides us with security while remembering a very small piece of information. Of course, you could have just compounded it, just concatenated it, and whatever. With this tree, you have like additional security measures, like you can just check out, the branches along the tree and have some very interesting properties. Since this presentation should be very short, I'll leave it at this. If you have any additional questions, we can discuss them later on. This was meant to be just a primer and get you into the mood for Bitcoin. So thanks. Any questions?